Happy Monday, everyone. So you should have gotten all the videos, well, access to all the videos on the same day, but if you're like me, you probably want it a bit more spaced out for you, so I'm going to call this the Monday Flipchart. So happy Monday, everyone. So I know that you haven't been given warm-up papers this week since you are learning from home, but I still like to start lessons with warm-ups. It gets us thinking about what we're going to be talking about. So today's warm-up is, what are some examples of physical and chemical changes? So there's a spot for physical, chemical changes. I would like you to please pause this video for a moment. Think of some examples of each. If you have a piece of paper, you can write it down, see if we come up with the same answers. Say it out loud, think it to yourself. But please pause here. I'm going to be quiet for a few seconds as well. So some examples of physical changes, where's my pen? There it is, would be changes of state. So boiling things, freezing, melting, just changing my physical state. So solid, liquid, and gas, any of those transitions. Another one would be tearing. Or tearing. So if I rip a piece of paper in half, that's a physical change. And crumbling, that's a U, crumbling, breaking apart. So you're just making something physically smaller. If I take one piece of paper, rip it in half, I still have paper. I didn't make something new. A chemical change is any time you make something new. So one chemical change would be lighting a candle. When I light a candle, I'm taking my wax, my candle wax, and I'm changing it, I'm combusting it into carbon dioxide and water vapor. I also can't undo my chemical changes. I can usually undo a lot of my physical changes, like boiling, freezing, melting. Depending on what you're tearing or crumbling, you might actually be able to undo that. So lighting a candle, rusting. Rusting is a chemical reaction. Baking. And to be honest, a lot of cooking. There are a lot of chemical reactions in cooking. You can't unfry an egg after all. And our suggested homework for tonight would be the balancing equations worksheet. At the end of this video, I am going to be going over some of the questions on that worksheet. If you still have the packet that was handed out before break, it's page number 23. Or I am also providing it as a PDF, a full-size PDF. It was a half sheet in your packet. So I'm providing a full-size PDF in the Monday folder as well. Of course, this is just your suggested homework. It is not actually due. But if you want to hopefully get that to count for other assignments, other missing homeworks, it does need to be in before I post an answer key. All right. So my agenda for this video is we've already gone over the warm-up. Next, we're going to start going over that new note packet. You have it in two different ways in this folder. It is there as a PDF. A PDF is going to keep the formatting that I tried really hard to give it. And you can print that out and fill in your notes on paper. I know I am a paper person. And I'm also providing you the newest note packet as a Google Doc. So if you're like me and you don't have a working printer, that might be your best idea. So the first part of the notes is just a rehashing of the physical versus chemical changes. Then we're going to go over the different parts of reactions, and then we're going to start balancing reactions. So this is the first part of page 1 of the notes. So physical changes, and a physical change, my chemical composition remains the same. It's just the appearance that may change. The appearance or the arrangement may change. So examples I said were changes of state like melting, freezing, boiling, dissolving things into water, crushing things, ripping things. Now in your note packet last fall, we actually had you draw this in. If you'd like to draw this in, there's a little bit of room on your note packet. But here I've got water, liquid water, boiling into water vapor. So I've got my water molecules here, 1 oxygen, 2 hydrogens. They're all relatively close, but not quite touching, so this is a liquid. And once I add heat, they space out. It's the same molecule, the big blue oxygen, the 2 little hydrogens, just are now spaced out. So this is a physical change. Their physical distance to each other changed, but my molecule is the same. But in a chemical change, the chemical composition changes. An entirely new substance is formed from what was there before. So this is all chemical reactions: rusting, corroding, neutralizing, decomposition are all examples of chemical reactions. So my reaction here is a fun one. It's hydrogen gas reacting with oxygen gas to form water. This makes quite an explosion. So here to start with, I've got my hydrogen molecules, H and H, and my oxygen molecules, O and O. They're attached to themselves. I've got a chemical bond between these 2 atoms and a chemical bond here. In order to make my brand new molecule, so notice my atoms are now attached to different things, I have to break and form new bonds. So atoms are rearranged, the atoms themselves, by the breaking and forming of chemical bonds. These 2 hydrogens were attached, but to come to here, now they have to be broken apart, and they form new bonds with an oxygen. These oxygens were attached. I have to break them apart. I have to break that chemical bond. And then by the time I get over here, 2 new hydrogens have attached themselves to that oxygen atom. So my molecules, my atoms, are being broken apart and put together back again differently. My molecules are different. Physical molecules are the same. Here, my molecules change. So for the next few sections, I'm going to keep referring to this reaction. It's one of my favorite. It's what happens when you react solid copper, like from a penny, with concentrated nitric acid, and we're going to get some dissolved copper nitrate, some gaseous nitrogen dioxide gas, and some liquid water. I used to always enjoy doing this as a demonstration for my students. It always came at quite a large personal cost of myself, a whole penny each year. So there's our penny. We've added the nitric acid, and already you can see the brown yellowish gas starting to form above it. Something else we learned about last fall is if you see bubbling, that's an indication of a chemical reaction. It means gas is being produced. That solution starts off a bit green, I believe, because it's a bit of a dirty penny, but pretty quickly I'm getting that very beautiful blue of a copper nitrate solution. And that nitrogen dioxide gas is a very irritating gas. Remember, if you can ever see the air that's coming towards you, that's not a good thing. And if you could reach into your laptop and actually touch that test tube, you'd also see that it's getting very warm. Another indication that there's been a chemical change is that they tend to make heat. They give off heat and feel warm, or a lot of times they will take in heat and feel very cold. All right, so the different parts. We have stuff on the left, an arrow, and stuff on the right of the arrow. So we always start with reactants. My reactants are what all chemical reactions start with, and they're what's on the left side of the arrow. So on left side of the arrow, what we begin with. And I also like to say that this is what is being changed. What is going through this change? What is being transformed? Then on the right side of the arrow, we have our products. So most simply put, this is on the right side. Right side of the arrow. It's what's left over at the end. It's what is made by this reaction. What is made or what is produced? Get it? Products produced by this reaction. It's what's left over at the end. And lastly, one more thing we should all be familiar with is the arrow itself. The arrow itself just means reacts. Sometimes you might see reacts to form. You might see yields. It can also mean produces. Reactions produce products. And we can also get some funky things going on with the arrow. Sometimes you might see a double arrow that looks like this. That just means I can go backwards and forwards. You won't be seeing that anytime soon, though. Sometimes you might see funky things like it takes some number of energy in order to take place. We can put a lot of little symbols on and over that arrow. We're just going to keep it basic for now. We're just going to keep a simple left to right arrow. Please, it's a small pet peeve of mine, please don't ever make it an equal sign. It's not an equal, it's a product. It starts with the reactants and it goes to the products. I start here and I end here. Before, then, after. Next, this should not be too new for anyone. We already took notes on this for our solution unit. But S means that something is a solid. L means that something is a liquid. Remember, you don't actually interact with too many liquids. Water is really the only liquid you tend to interact with. Most things are actually solutions. G means gas. And AQ should be still fresh in everyone's mind. Just means aqueous. And if you've forgotten what that means dissolved. And it's almost always dissolved in water. The further you go into chemistry, more and more complex stuff, you might start dissolving things in stuff that isn't water. But as long as you're in honors chemistry, we're going to keep it simple. We're going to keep it dissolved in water. So next are the coefficients. So right here in front of my copper, I don't have anything written. It's just like subscripts. Nothing there means 1. So my coefficients are the big numbers in front of each chemical formula, in front of each chemical compound. And the important thing is that they tell us how many we need of each compound. So coefficients are big numbers that tell us how many of each compound we need. And as a small fact, you might want to write this down as well, it acts like a multiplier. You should have had some practice with this in the counting atoms worksheets back when we were learning molar mass, but just like this 2 affects everything on the inside, my coefficient affects everything right behind it. So it multiplies the atoms, or the number of atoms in each compound. You know, I'm going to cross out each. I'm going to say in its compound. Okay, so let's do some counting here. I have nothing written in front of my copper, so that means it is a coefficient of 1. No subscript also means a subscript of 1, so I start with just 1 copper. You know, I'm not loving that color. Let's go to purple. 1 copper. Then on the other side, again, I have no coefficient in front of my copper. I have no subscript, so that's 1. So 1 times 1 means on this side, I have 1 copper again. Sorry, just trying to get it to look a little bit more visible. Here we go. 1. There we go. Now for hydrogen. Here I have 4 hydrogens times a subscript of 1. So I have a total of 4 hydrogens. On this side, oh, there's my hydrogens. Okay, I have 2 hydrogens in each water, but I have 2 waters, so 2 times 2 means I have a total of 4 hydrogens. Nitrogens, over here, I've got a coefficient of 4, subscript of 1, so 4 times 1 gives me 4. On this side, ooh, it's going to get a little bit more complicated now. So I've got nitrate. There's only 1 nitrogen in nitrate, but I have 2 nitrates per copper nitrate, so that's 2 times 1. So I've got 2 nitrates here. Sorry, 2 nitrogens here. Coefficient of 1. So 1 times 2 gives me 2 nitrogens. Then I've got another nitrogen over here, nitrogen dioxide. No subscript here, so that's just 1. But my coefficient is a 2, so 2 times my 1 gives me 2. So I have a total of 4 nitrogens in my products. Now my oxygens. I have a subscript of 3 here in my nitric acid times 4 nitric acid, so I have a total of 4 oxygens. Sorry, total of 4 times 3 oxygens, so I have a total of 12 oxygens. Then on the product side, I have 3 oxygens per nitrate, 2 nitrates per compound, so 2 times 3 gives me 6. 6 times my coefficient of 1 gives me 6 oxygens. Then I've got more oxygens here, 2 oxygens per compound, but my coefficient is a 2, so 2 times 2 gives me 4. And then here in water, I've got no subscript, so it's just a 1 times my coefficient of 2, so that's a 2. So I add all of this up, 6 plus 4 gives me 10, plus 2 gives me 12 oxygens. Now, a very important thing I have not mentioned yet is I always need to start and end with the same number of atoms. I started and ended with 1 copper, started and ended with 4 hydrogens, 4 nitrogens, 4 nitrogens, 12 oxygens, 12 oxygens. It's because of something called the conservation of matter, or sometimes it's also known as conservation of mass. We cannot gain or destroy matter during a chemical reaction. So gained, or that shouldn't say gained or created, that should be gained or destroyed. Cannot be gained or destroyed during a chemical reaction. What goes in must come out. I can't say I have enough supplies to make 2 grilled cheese sandwiches and then come out of the kitchen with 27. It also, if I said I'm going to make as many grilled cheese sandwiches as possible and I have enough to make 2, it doesn't make sense if I then walk out with just 1 regular grilled cheese sandwich. My ingredients and my final products need to be the same, so I need to start and end with the same number of each atom. So they must have the same number of atoms on either side of the reaction. We started and ended with the same numbers of coppers, hydrogens, nitrogens, and oxygen. And the way we do this is by changing the coefficients, by changing the number of atoms total. So here is my first example problem. So H2, and this is a good strategy. It's what I like to do. I like to draw the atoms themselves. It helps to visualize how much I have. Ooh, that's not what I wanted. So there's my H2, there's my O2, here's my H2O. Another thing I like to do is to make a table to help organize what I'm doing. So here I have hydrogens and I have oxygens. Now to start on this side of the arrow, I have 2 hydrogens. I have 2 oxygens. And on this side of my arrow, on the right side, I have 2 hydrogens and I have 1 oxygen. So this is not balanced. So I'm going to change my coefficients so I have equal numbers on either side. My problem seems to be on this side. I don't have enough oxygens. So I'm going to add another oxygen here. Sorry, I can't add just an oxygen. I'm adding a whole nother water molecule. So instead of a coefficient of 1, I now have 2 molecules of H2O. 1 molecule, 2 molecules. It comes as a set. So now my numbers of atoms have changed. I now have 1, 2, 3, 4 hydrogens. And I now have 1, 2 oxygens. Ooh, what's going on with my pen? I now have 2 oxygens. Also, 2 times 2 gives me 4, and 2 times 1 gives me 2. But now, my oxygens are happy and equal. 2 oxygens to start, 2 oxygens to finish. But now my hydrogens are not balanced. I have 2 hydrogens to start and 4 hydrogens to finish. Well, my hydrogens come in sets of 2, so let me add another one. So now I have 2 molecules of hydrogen gas here. So 2 times 2 gives me 4. And this is why I like drawing it out, because I can also count it. 2 molecules of H2, 1, 2, 3, 4 H's. So now, probably one of the most important things to write down on page 2 of your notes are my rules for balancing. This goes through what I just did, but I really love giving you numbered lists. So rule number 1 is count up the atoms on each side of your equation. So notice what I did was I counted how many hydrogens, how many oxygens I had on either side. Now, almost every rule here now also has a sub-rule. So in parentheses, I would put in, don't break up those polyatomic ions unless you have to. You are most likely not going to get a reaction during this unit where you need to actually break apart those polyatomic ions. If you have a carbonate on one side, you're probably going to have a carbonate on the other side of your equation. So rather than counting it as 1 carbon and 3 oxygens on either side, it's going to make your life a lot easier if you count it as 1 carbonate on either side of the equation. Next, find out which atom you need more of and change its coefficient. So we saw that we needed more oxygen. We had equal amounts of hydrogen on either side, but it was the oxygen we needed more of. So we changed the coefficient of that water molecule. Now my sub-rule here is, if you have a lot of different elements that you need to balance, sometimes you only need to balance 1 to begin with. Sometimes there's multiple atoms that are not balanced. Start with carbon. If you get a choice, balance your carbon first and then balance your other atoms, your other elements. And then the last step is to repeat 1 and 2. Always add up your totals each time you change a coefficient, and keep repeating 1 and 2, 1 and 2 until everything is equal. It's kind of a back and forth. It's kind of why I like the seesaw idea here, is because you're going to unbalance it before you balance it. And again, if you get the choice, you should always balance out your carbon atoms first, and you should always balance out your oxygens last. If you try to start by balancing your oxygens, you often get into a place where you can't actually solve your question. But if you wait until the end to balance your oxygens, take care of everyone else, you're going to have a much easier time. All right. So this is the first problem, I believe, on that balancing equations worksheet. So I'm going to go through these steps. I'm going to make my molecules here. Notice I have SO4. I've got sulfate here. I'm not counting it as oxygen and sulfur. I'm counting it as sulfate because I have sulfate on this side and I have sulfate on that side. Okay, and I'm going to make a little table here. So I have on either side of my equation my lead, I have chlorine, I have sodium, and I have my sulfate. It is surprisingly difficult to draw a straight line on a slate. All right, so to start, I have one lead atom. I have 2 chlorines. I have 2 sodiums. And I have 1 sulfate. Then on my other side, on my product side, I have 1 lead, 1 chlorine, 1 sodium, and 1 sulfate. So that was step 1. I have counted all of the atoms that I start and end with. So now I need to find one atom that needs to be balanced and change its coefficient. So I can start with either calcium or sodium, chloride or sodium. I'm going to choose the chloride because I saw it first. So over here on my product side, this is where I find my chloride. So I only have 1, so let's add another molecule. So if I add another NaCl, that changes my coefficient to a 2. So now I have 2 sodiums and 2 chlorides. So I changed my 1 chloride into 2. And I changed, oh wait, that doesn't just change my chlorine, that also changes my sodium. So my sodium went from 1 to a 2, which solves our problem here. Now I've got 2 chlorides on either side and 2 sodiums on either side. Remember, when you change your coefficient, you're not just changing one thing. So step 2 was to change the coefficient so it's equal to what you need it to be. So I changed it to a 2 because 2 times 1 gave me the 2 atoms of chloride I wanted. And that also affected my sodium. So I didn't need to go back and change anything else because that actually finished. I didn't really need to worry about step number 3 of rinsing and repeating. So I'm going to work through another 2, the next 2, number 3 and number 4 on that worksheet. See, I've got a silicon, I've got 2 chlorides, 2 chlorines, then I've got a silicon tetrachloride. So I'm going to make my table, I'm going to make it a skinnier table. So let's see, I've got silicon and chlorine. I start with 1 silicon. I start with 2 chlorines. I end with 1 silicon, and I end with 4 chlorines. So I've done step 1. Step 2 is figure out which atom I need more of and change its coefficient. So my silicons, I start and end with 1 of those each, so I don't need to worry about that. But my chlorine, I start with 2 chlorines and I end with 4 chlorines. So I need to change my coefficient. So each time, you know what, rather than grab it from here, let me use another trick. I need an entire new chlorine molecule. Because remember, I can't just add 1 chlorine at a time, I have to add that entire molecule. So now I have 1, 2, 3, 4. Oh, hey, that's how many I need to balance my reaction. So I have 2 molecules of my chlorine. So 2 times 2 gives me 4. And now I'm balanced. 1, 1, 4, 4. All right, here, let me do the next one. I'm going to leave the rest to you guys. Ooh, this already looks just a little bit more complicated. But I think we can still do this. Let's see. I've got chlorine, I've got my potassium, and I've got my bromine. So to start, I start with 2 chlorines, 1 potassium, 1 bromine, and to finish, I've got 1 chlorine, 1 potassium, and 2 bromines. Oh, I wrote the wrong number for bromine to start with, sorry. I start with 1 bromine. All right, so now I can either start by balancing my chlorines or my bromines. Rule number 2 said if carbon is an option, I should start balancing my carbon, but I don't have any carbons. It also says to balance oxygen last, but I don't have any oxygens. I'm going to start with my chlorine just because it's the first one on this list that needs to have more of. So I need more on my product side, so I come over to my product side, and there is my compound with chlorine. So I'm going to take that and duplicate it. So now I've got the same molecule 2 times. 1, 2 chlorines. Oh, hey, that was easy. That wasn't too bad. So that's a coefficient of 2. So 2 times my 1 subscript gives me 2 chlorines. Awesome. Now my chlorines are balanced, but oh, shoot, wait. 2 times the 1 coefficient for my potassium. So my potassiums were nice and balanced. Now they are not. Now, rather than jumping to BR, what you should do is, this was balanced, but by balancing my chlorine, I've unbalanced my potassium. So rather than look for something else to fix, I'm going to fix what I just screwed up. My potassium was good, my potassium was balanced, but I screwed that up. So I'm going to come over here, and I'm going to fix it. So I've got 1 potassium in this molecule. So I'm going to make 1 more of that molecule. Now I've got 2 potassiums. Awesome. So now my coefficient is a 2. 2 times 1 means that I have 2 potassiums. Yes, my potassium is balanced. Shoot, wait. If it multiplies my potassiums, it multiplies my bromides. I've got 2 bromides. Okay, well, you need to update your table. This is how we keep track. Oh, hey, look. By balancing my potassiums, I balanced my bromines. When you choose one thing, balance it, fix whatever you unbalanced, and then keep going back and forth, fixing whatever you unbalanced, you usually end up by your last balancing to solve more than just 1 atom. I do want to point out it's a little weird that I ended and started with 2 of each type of atom. It doesn't always happen like that. For number 3, I have 1 silicon and 4 chlorines on either side. It just depends on that element itself. Okay, well, I hope you enjoyed this video lesson. We are all available via email and during our posted office hours.